It's 8:30. Let's go and get started. All right, good morning, everybody. How's everyone doing today? Everyone had a good long weekend, hopefully? Caught up on work, probably. That's probably how we all spent our day off yesterday, but you know, hopefully it was restful at least. Okay, so today we're going to be continuing on with Laplace. Okay, so it's nothing exciting, but today we're actually going to be solving some equations today. I do need to go a little bit fast today, just because something was kind of sprung up on me on Friday that we have a lot of guest speakers coming on Thursday, and they needed people to open up their lectures for them. So I was kind of selected to have a guest speaker on Thursday, and so we won't have a usual lecture. And so I need to go a little bit faster just to make sure that you guys can get a good head start on homework, and just so that we're kind of still in a good position for next week. Okay. So that's happening on Thursday. So Thursday we have a guest lecturer. I have no idea who it is. I'll probably find out probably same time as you guys, probably on Thursday morning, and someone just shows up here. But supposedly we have a guest lecturer on Thursday, and they're going to take up the class. Okay. So it's all part of ECS week. So if you're not aware, this is ECS week. And so usually on Thursday of ECS week, we have guest lecturers come. These are usually alumni or people, you know, who have connections to the school, or worked in industry for anywhere between like 5, 10, 15 years. And so during this time, they like to come to the lectures and talk a bit about the work that they do, talk maybe a bit about their experience at Cal State Fullerton, and maybe give some tips in terms of, you know, how to get out there in the workforce. Okay? So come Thursday, you know, my experience with these guest lectures that they're always really good. They usually bring a presentation of about maybe 40, 45 minutes. And then the rest of the time, they just open up for questions. So if you want to talk to an alumni, question, is the guest lecture going to be on Zoom too? Yes, that's the plan. So the guest lecture will also be on. Yeah, so you'll just use the regular Zoom link. Yeah, so definitely come with your questions on Thursday. You know, you can ask them questions like, how'd you get a job? You know, what's your experience at Cal State Fullerton? We're all the shitty professors, you know, they'll tell you that. They'll say this guy's the shittiest one. You know, anything. So, you know, definitely come Thursday, and you know, it'll be a good experience. All right. And because of the guest lecture, I am pushing the due date for homework 3 back just a little bit. So normally, you know, our homeworks are typically due on Fridays. But I think, you know, we'll be covering stuff that's in homework 3 up until Thursday of next week. So I don't want to cover something on Thursday and have it due immediately the next day. And so I'm pushing it back until Sunday. It's hard for me to push it back a bit more because our midterm exam is going to be the following week. And so I want to make sure I have your homework 3 graded and have the solutions out to you at least 2 or 3 days before the exam so that you can actually do that study. Okay. So Sunday, I think, is about as far as I can push it. But you know, I'll try to get through everything so you can do as much of homework 3 as you can before next week. Okay. All right. Any questions on anything before we get started for today? Okay. All right. Let's go ahead and get started. All right. So we're kind of right smack dab in the middle of covering Laplace transform. Right? So so far what we've covered is you know, just defining what the heck the Laplace transform is. We've talked about the forward transformation and the inverse transformation. Okay. So I think at this point, you know, we're fairly comfortable with that. So now we're getting to the point where we can actually start using this to solve differential equations. That's ultimately our goal. Okay? But before we can really get into that and start doing examples for that, we need to talk about partial fraction decomposition. Okay. Right. So partial fraction decomposition, have you guys seen that before, maybe in a previous math class before? It at least sounds familiar. I know maybe you don't remember how to do it, but it at least sounds familiar. Okay. So the idea behind partial fraction decomposition is that, you know, if you have a very complex denominator with, you know, a lot of terms multiplied by each other, partial fraction decomposition gives you a way to take that complex denominator and break it up into simpler terms. And so the reason we need this for Laplace is that, when we start to apply Laplace transforms to differential equations, you're going to end up with a lot of fractional terms with a very complex denominator. Okay. All right. So I think the best way to illustrate this is just to kind of jump right into an example. Okay. All right. So let's say that, we are, solving a differential equation with Laplace, and we end up with the following Laplace expression. And so what we want to do is we want to take the inverse Laplace of f of s is equal to 3s plus 2 on over x squared plus s. Okay. So this is a pretty typical expression. And so, you'll definitely see something like this when you start applying it to differential equations. Okay. So remember how we take the inverse Laplace. So typically when we take the inverse Laplace, what we do is that we work on this expression and try to get it to match, or at least to look similar to something in our Laplace table. Okay. And so, the first thing you should do when you see an expression like this is to look at your Laplace table and check and see if this looks similar to any of the expressions in the table. And so basically what we're going to be looking for is there any Laplace expression with an s squared plus s on the top? Okay. And so the thing, remember, when you have Laplace expressions, s is kind of your main variable of focus. And so, you should try to look for expressions with the same structure of s. Okay. And so for a function like this, we'd be looking for something with s squared plus s in the denominator. Unfortunately, you can look at the table all you want. There is nothing with s squared plus s in the denominator or anything even remotely close to that. Okay. And so we're going to have to break this apart. Okay. So first thing I'm going to do is I'm going to take the denominator and I'm going to factor an s out. So we have an s times s plus 1. So I took the common term of s and just factored it out. And so why is this significant? And so if we look at this, and so if we say, okay, we have kind of two terms in our denominator here. We have kind of a 1 over s term, okay, and a 1 over s plus 1. I know the numerator is different, but the numerator, we have a lot more flexibility with the numerator. So we don't have to worry about that just yet. All right, but if we look at our denominator, we can say that we can break that up into two terms, or theoretically, if we could. And the nice thing about this is that if we look at 1 over s and 1 over s plus 1, both of these are in the table, right? Or we have expressions in our Laplace table that look similar to these. And so we can take this Laplace expression and break it up into two fractions, where one fraction has a denominator of s and the other fraction has a denominator of s plus 1. Then we'd be in good shape, because then we can actually start to take the inverse. So basically what we want to do this. And so we have our original fraction. Okay. So our original fraction is 3s plus 2 over s times s plus 1. And what we want to do is we want to decompose this. And so we want to decompose it into two separate terms, okay? A over s and b over s plus 1. Okay? Where, the reason we do this is that, if we can break this up into these two separate terms, separated by plus signs, then we can actually start to take the inverses. Okay? So that's the idea with partial fraction decomposition, is to take a complicated Laplace expression, something that you're probably not likely to find in the table, but then break it up into terms that you can find in the table, so that you can take the inverse Laplace, the Laplace. Okay. Of course, now the question is, A and B. I kind of just made those up right now. In order to properly perform this decomposition, we need to solve for what A and B are. All right, any questions on this so far? Okay. All right, so let's solve for A and B. All right. So the way that we solve for the numerator is that we basically take this expression and we eliminate all the fractions. Okay? And so the way that we do that is we're going to multiply by the total denominator. Okay? Okay. And so our total denominator here, or the left-hand side denominator, is s times s plus 1. And so let's multiply this entire equation by that. So the idea is that, on the left-hand side, we want to eliminate that denominator. And so we're going to multiply by that. Okay? And so I'm going to take this entire equation here. Okay? And I'm going to multiply by s times s plus 1. Okay? And so that's going to be multiplied by both the left-hand side and the right-hand side. And because we're doing it to both sides of the equation, this is a valid algebraic operation. Okay, and so if we carry out that multiplication, on the left-hand side, it's going to completely cancel out with the denominator, which is exactly what we want. And so we're left with 3s plus 2 on the left-hand side. And then on the right-hand side, because we've decomposed this, we're only going to get partial cancellation on the A and B term. Okay? And so for the A term, the S is going to cancel out with this S. And so we have A times S plus 1 plus B. And for B, since B is over S plus 1, that's going to cancel out with that. We have B times S. And now what we have right here is an algebraic expression. And so if you remember the technique that we used with unknown coefficients in the second order ODEs, basically what we're going to do here is we're going to group the like terms and use those to solve for A and B. So let's group the like terms. And so the left-hand side is still going to be the same. So we have 3s plus 2. And so I'm going to take all the S terms. Okay. For the S terms, we have just A plus B. And then for the constants, we have just A. And so at this point, what we can do is we can set up our system of equations to solve for A and B. Okay. And so we're going to equate the S terms. And so everything multiplied by S on the left-hand side is just 3. And that's going to be equal to A plus B. Okay. And then for the constant term, on the left-hand side, we have 2. And on the right-hand side, we have A. So this is a pretty simple system. And so from the second equation, we can see that A is equal to 2. We plug that into the first equation right here. We have 3 is equal to 2 plus B. So this tells us that B is equal to 1. All right. So now that we've solved for A and B, let's go ahead and plug it back into our original decomposition. Okay. And so if we look back up here, our original decomposition looks like this. Okay. And so we have 3s plus 2 for s over s plus 1 is equal to a over s. And so we have a is equal to 2. And then b over s plus 1 plus 1 over s. Right. So now that we've decomposed the denominator, we can invert it. Okay. And so first we have 2 over s. And so we know 2 over s, we factor out the 2. This ends up as, so we have 2 equal 2. Okay. We know the inverse Laplace of 1 over s is just 1. And so if we multiply that by 2, that becomes just 2. And then we have 1 over s plus 1. And because of the, well, in this case, it's just an exponential function, but you can also say it's due to the first shifting theorem. Okay. This ends up being E. So both of those inversions, I just did those really quickly because those are just, you can just look those up easily in the table. Right, and so that's the idea with partial fraction decomposition. And so, you're going to end up, once we start solving equations, you're going to end up with terms with very complex denominators. And so you can use partial fraction decomposition to break it up and get them into terms that you can just easily invert. Okay. And so, I would say that most of the work that you do in Laplace problems, especially for differential equations, is going to be doing the partial fraction decomposition. Okay. And so technically speaking, partial fraction decomposition is just algebra. That's what people say, but it can be pretty tedious. This example wasn't too bad, but we'll do a couple more examples where there's a bit more work, and you can see it gets a little bit gnarly. But before we do that, are there any questions on this example here? Okay, all right. So let's do another example. This one a little bit more complex. So same thing, same idea as the previous example. And so we want to find the inverse Laplace of the following function. Okay, so we have f of s is equal to s squared plus 1 up top. And then in the denominator, we have s times s minus 1 cubed. All right. So a bit more work. Yes, question. Yeah, because from the table we have e to the at, and what we say is that inverse or that Laplace transform is 1 over s minus a. And so that there's kind of a sign flip when you go from Laplace domain or from physical domain to Laplace domain. So you go s plus 1, it ends up being a minus 2. Minus 1, it will still be equal to 2. No, if it was s minus 1. If it was s minus 1, it would be e to the positive 2. Yeah, so it's just opposite signs in physical domain and Laplace domain. Okay. All right. So back to this example. So we have quite a complex denominator here. Okay. And kind of the big difference here is that we have an s minus 1 cubed on the bottom. And so what we can say, or one way to say this, is that we have s minus 1 appearing 3 times in the denominator. And so we need to account for that when we take our partial fraction decomposition. All right, let's go ahead and do that. So let's do our partial fraction. Partial fraction decomp. Right, and so on the one side, we have s squared plus 1 for s minus 1 cubed. Okay. And so if we follow the same logic as last time, we have a over s, okay, plus b over s minus 1 cubed. Okay. Okay, that's what we would normally do. But when you have a term that shows up kind of more than once like this, okay, so we have an s minus 1 cubed, we have to account for all the lower powers of that term. And so that means we actually have 4 terms in our decomposition. And I'm going to erase this just so it matches up with my notes, so I don't make any mistake. Okay. And so we're going to have c for s minus 1 squared plus d over s minus 1. Okay. And so notice that s minus 1 cubed became 3 different terms. So we have s minus 1, s minus 1 squared, and s minus 1 cubed. Okay. Because remember, the other way that you can write this is like this. So s minus 1, s minus 1, s minus 1. So it really is kind of like 3 terms in that denominator. Okay? And so that means our decomposition should also have, 3 terms associated with that. But because it's kind of a repeated term, and we have to make sure that each of the terms here are linearly independent from each other, we make sure that all the terms in the denominator have a different exponent. And so the d has an s minus 1, the c term has an s minus 1 squared, and the d term has an s minus 1 cubed. Okay. Okay. So that's kind of the only twist on this problem, besides the fact that it's going to be a lot more work. But from here, we're going to follow the same process that we did before. So we're going to multiply by the denominator, we're going to group the like terms, and we're going to solve for the coefficients. Okay. Are there any questions on kind of how we set this one up here? Okay. All right, so let's go ahead and do the same thing. Let's multiply by the denominator. And so the left-hand side denominator in this case is s times s minus 1 cubed. Okay. So let's go ahead and distribute that through the entire equation. So on the left-hand side, we have s squared plus 1. Okay, so we're going to have a total cancellation of the denominator. We have a. The s is going to cancel out with that s, but then we're still left with an s minus 1 cubed. Okay. Then we have b. One of the s minus 1s is going to cancel out. But we have also an s there, so we have an s times s minus 1 squared. Okay. Plus c. We have an s minus 1 squared on the bottom of c, and so that's going to cancel out with 2 of the s minus 1 cubes. So we're still left with 1. We have s minus 1 plus d. Okay. And so for the d, we have an s minus 1 cubed on the bottom. That's going to cancel out with an s minus 1 cubed up top. And so all we're left with is an s. Okay. And so from here, we have quite a lot of foiling to do. And so first, let's FOIL everything out. And then after we FOIL everything out, let's group the like terms. S squared plus 1. First, we have a times s minus 1 cubed. And so that's going to be, if we completely FOIL that out, minus 3s squared plus 3s plus 1 plus b times s cubed minus 2s squared plus s plus c s squared plus s plus d s. All right. So the next step, we've done this before. So let's take all the like terms in terms of s cubed, s squared, s, and the constant, and group them all together. So on the left-hand side, we still have s squared plus 1. Okay. Then we have s cubed. So maybe you do this already, but I like to do this when I have when I'm grouping the like terms and I have kind of a lot of stuff going on. I like to cross out the terms as I kind of write them down. Okay. All right. So first we have s cubed. And so for s cubed, we have an a. Okay. And so once I mark down that I have an a for s cubed, I basically cross this out right there. Okay. That's just to make sure that I don't double count it, so I don't count the same term twice. And it's also kind of good at the end to make sure that I account for all the terms. Okay. You don't have to do this. I do this just because it helps me keep organized. But for me, it helps a lot. So I thought I'd let you guys know. Okay. And then we have another s cubed term, which is b. We have s cubed times a plus b. All right. And so now we have the s squared terms. And so for s squared, we have a minus 3a. We also have a minus 2b. And then a plus c. So those are all the s squared terms that we have. Then we have the s terms, and so for s, we have a positive 3a. We have a positive b. And a c. And a positive d. And then finally, we have the constant term. We just have one term left. And we just have a minus a for that. And so by grouping the like terms, you can see we have 4 different expressions in the parentheses. And so that's going to give us our 4 equations to solve for those 4 unknowns. So let's go ahead and set up our equations. We have s cubed, squared, s, and the constant. Okay. So s cubed first. On the left-hand side, we have 0, because s cubed doesn't appear on the left-hand side. That's equal to a plus b. Okay. Then we have the s squared term. On the left-hand side, we have a coefficient of 1 in front of s squared. And on the right-hand side, we have a minus 3a, plus 2b, plus c. Okay. Excuse me. For the s term, we don't, s does not show up on the left-hand side either. And so that's going to be a 0 on the left-hand side. On the right-hand side, we have a 3a, b, c, d. And then finally, for the constant term, we have just a plus 1 on the left-hand side. And so that's just going to be end up with a 1. And on the right-hand side, we have a minus a. Right, 4 equations, 4 unknowns. This one's not terrible. I mean, we have the last equation to kind of start with, and then everything just kind of cascades from there. Okay, so let's go ahead and solve this equation for A, B, C, and D. From this very last equation right here, we have A is equal to minus 1. That's kind of a gimme. And so now that we have a solution for A, let's see where we can plug that back in and solve for another constant easily. Okay. If we look at the first equation in our system here, we have just an equation that involves A and B. Okay? But if we know A already, then B is really easy to solve. And so we have 0 is equal to minus 1 plus B. This tells us that B is equal to 1. Now let's take our expressions for A and B, plug it into the third equation. Okay. Because the third equation involves A, B, and C. But since we know A and B, that means C is going to be easy to solve for. Okay. And so if we solve for C, what we get is 1 is equal to minus 3 times A. So that's going to be a positive 3 minus 2B plus C. Okay, so if we solve from C, see that C actually equals to 0. Okay. And then finally, we can plug everything else into equation 3. And so equation 3 is going to let us solve for D. All right, so we have 0 is equal to minus 3 times A. A is minus 1, so it's minus 3, plus B, which is 1, minus C, which is 0, plus D. And so this tells us that B is equal to positive 2. Yeah. So now that we have the values for A, B, C, and D, we can plug this back into our original decomposition. And so our original decomposition was S squared plus 1 all over S minus 1 cubed. Okay. Right, so let's plug in A, B, C, and D. And so let's plug in A first. As we have a minus 1 over S. Then we have B, which is 1, so that's going to be 1 over S minus 1. C is 0, so let's go ahead and ignore that. And then we have D, which is 2 over S minus 1. Right. All right, final step, and then I'll pause for questions. And so the final step is just take the inverse of this using the table. And so we take the inverse of this, get f of t is equal to inverse of minus 1 over s is just a minus 1. Inverse of 1 over s minus 1, that's just going to be a positive e to the t. Okay. And then inverse of 2 over s minus 1 cubed, this is a function for t squared with the shift. And the shift is a e to the t. right? So a bit more complicated of an example. And so this one I think is more kind of typical of what you'll see for a differential equation. Okay. All right, any questions on this example here? All right. So we've done two examples today of partial fraction decomp. I have one more example I want to do today, just to kind of show you one more look. Okay? So what was different from this example, remember, is that we had kind of a triple, almost like a triple root on the denominator. So we had s-1 appearing 3 times. And so, you know, we learned from this example that we had to account for it 3 times with 3 different terms in the decomposition. Okay? For this last example that I'm going to do with partial fraction decomposition, I'm going to show you what happens when you have a denominator that can't be factored. Okay, so this is going to be example 3 of partial fraction decomp. So I'm going to find the inverse of f of s is equal to s minus 3 over s cubed plus 3s. Okay. So a little bit similar to the first example that we did, but there is kind of a wrinkle. Okay. So let's start out by factoring out s. Excuse me. Equal to s minus 3 divided by s squared plus 3. Okay. So we factored out an s, which is good, but we can't really factor this anymore because we have s squared plus 3. That one's kind of unfactorable. Okay, but we still want to decompose this. And so we have s minus 3 over s squared plus 3. And so we can see immediately that we have a 1 over s on the left-hand side, and so that's going to be an a over s. Okay. And then we have the s squared plus 3. Okay. So normally what you would do is you would do just b over s squared plus 3, right? So we just take some unknown numerator, b, and then put it over our denominator. Okay. Normally that's what you would do, but when you decompose a fraction like this, the numerator and the denominator often have to be just kind of one order apart. Okay? And so if we look at this expression here, s squared plus 3, this has polynomial order of 2. Okay. Because we basically couldn't factor it anymore. And so if our denominator here has order of 2, then our numerator has to have order of 1. Okay. And so instead of b, we're going to do bx. Okay. Okay. And we need to have a constant term. So we're going to have bs plus c. Okay. So we have three coefficients to solve for in this case. So a, the b, and the c. So this is typically what you do when you have an unfactorable denominator. So if you have some kind of s squared plus something on the denominator that you can't factor anymore into separate roots, that's fine. That's going to happen. But all you have to do is just account for it in the numerator to make sure that you have a linear polynomial. Okay. And so instead of just b over s squared plus 3, we have bs plus c over s squared plus 3. All right, any questions on this? Okay, But from here, we're going to follow the same process. So let's multiply by the denominator. And so we multiply by the denominator on the left-hand side, we have s minus 3. Okay. Because we know on the left-hand side, what we multiply by is going to cancel that out completely. Then we have a, the s is going to cancel out with the s, and then all we're left out with is s squared plus 3. And then we have bs plus c. The s squared plus 3 in the denominator is going to cancel out with their s squared plus 3. And so all we're left with is just an s for the bs plus c. I'm going to go a little bit more quickly this time, just because it's kind of just going through the motions here. But just like before, let's group the like terms. We have s minus 3 is equal to. First, we have the s squared term. S squared is going to be a plus b. Okay. Plus s. We only have one s term, which is the c, plus the constant term, which is just 3a. Okay. All right, and so just like before, we can go ahead and set up our equations. Squared s and the constant term. So s squared on the left-hand side, we don't have a term. And so that's just going to be 0. On the right-hand side, we have a plus b. Okay. For the s term, we have a coefficient of 1 on the left-hand side. So that's going to be equal to c on the right-hand side. And then for the constant term, we have minus 3 is equal to 3a. So now that we're at this point, this system's pretty easy to solve because equations 2 and 3 just can be solved straight up. Okay? And so for equation 2, we get that c is equal to 1. For equation 3, we get that a minus 1. Okay? And if we plug in a into equation 1, then we get e is equal to. Okay. And so our decomposition for this, we started with s minus 3 for s times s squared plus 3. And so our decomposition of this is we have a minus 1 over s plus b times s. And so since b is 1, we have s over s squared plus 3. And then plus c, which is just 1. Okay. And now we're good because now we can invert this. Okay. One thing I'll do really quickly, just because we don't have any shifts here, I'm going to go ahead and separate this out into its own term. Okay. So all I did was I took that plus 1 up top on the s squared plus 3 term, and I just separated it out into its own term just so we can invert it separately. And finally, we can just invert this. Okay. All right, so first we have the inversion of 1 over s, minus 1 over s, and so that's just a minus 1. Then we have the inversion of s over s squared plus 3. And so we have s over s squared plus omega squared. And so this looks like a cosine term. Okay. This is going to be cosine square root of 3 times t. Okay. We have kind of a weird frequency here because it's s squared plus 3. But remember, you know, the standard form for cosine is s over s squared plus omega squared. So the actual omega, the frequency, is going to be square root of. Okay. And then we have this term. We have to work on this term a little bit, okay? Because if we look in the table for the Laplace transform of sine omega t, what we get is omega over s squared plus omega. Okay. That means that if we want to take the inverse, and we know this looks like sine because we have a constant up top. Okay? In order to get this to be in the right form, we need omega up top. Right? And so what I'm going to do is I'm going to do my multiply by 1 trick. And so in the parentheses here, I'll have square root of 3 divided by s squared plus 3. Okay. So that one we can directly invert. We can't pull that square root of 3 out of nowhere. And so we need to divide by square root of 3 in order to make that work. Okay. And so the inversion for this is going to be 1 over root 3 times sine square root of 3 t. Okay. All right, any questions on it? Yeah.
How would the opposition look like if the denominator would be like a higher order?
Yeah, good question. So if the if we had a function like this, let's say it was like, you know, s plus 3 over s times s cubed plus 4 or something like this. And so you would just add an additional term up top, a over s plus. And so instead of a linear polynomial, you have a quadratic one. We have b s squared cs plus b s cubed plus. So you just want to make sure they're all just kind of one off. The question?
And then if that s cubed plus 4 quantity was squared, you'd need like es squared plus like whatever, like, and then the bottom like squared.
Yes, yeah, and then that would go back to example 2. So you need kind of two. You need 2 of these guys right here, because you need one for just s cubed plus 4 by itself, and then another term that's s cubed plus 4 squared. So yeah, it gets to be quite a lot. Is there a question over there too? Okay. Yeah, but you won't. You know, I'll say that, you know, it usually doesn't get much worse than these ones. So theoretically, you know, that's what you would do, but yeah, but for the purpose of solving differential equations, it usually doesn't get worse than the 3 examples that we did. All right, Zoom, any questions? I make sure to pause because I know it takes a while to type questions on Zoom sometimes. Okay. All right, so that's partial fraction decomposition. So, you know, we're going to be using that a lot. So the last thing I want to do today, so I have 2 more examples. So today is just kind of full of examples. Let's actually solve some differential equations, okay? And so if you look at the homework, homework 3 is posted. It is the lengthiest homework, I would say. Problems 2 and 3 involve, problem 2 is just taking the Laplace transform or the inverse. So you should be able to do that one already. Problem 3 is solving actually differential equations with Laplace. Okay? And so my hope is that after today, you should be able to do problems 2 and 3 on the floor. Okay? 4 and 5 involve step and impulse functions, and so we'll go over that next week. But I want to make sure that you can do differential equations after. So let's do a couple of examples. Okay, so let's start out with a fairly simple example. Okay. So let's solve this initial value problem. So I'll call it IVP. And so initial value problem has our differential equation. So in this case, it's going to be y squared minus y equals t. Okay. In addition to this, we're going to have our initial conditions. So we have y of 0 is equal to 1. Then y prime of 0 also equal to 1. And so we want to solve this equation or solve this differential equation using Laplace. Okay? You could absolutely do this with our normal methods. And so there's nothing crazy here yet. We haven't gotten to step in impulse functions yet. And so you could absolutely solve this using the normal way. But let's solve it using Laplace just so that you can kind of see how it's done. Okay, and so if you remember from last Thursday, there's kind of a 3-step process to solving a differential equation with Laplace. So step one is to take the Laplace transform of the entire equation. And so here you're going to need to use the Laplace transform of derivatives, right? So we have the Laplace transform of y double prime. And so if you remember what that is, this is s squared y of s minus s times y of 0 minus y prime of 0. So all of this is the Laplace transform of y double prime. And then we have the Laplace transform of y. And so that one's not a derivative. And so we don't need to do anything special. And so this is just going to be y, big Y of s. Okay, so this right here is the Laplace transform of y. And then we have the Laplace transform of t. And so the Laplace transform of t is 1 over s squared. And that you could look up in the table. So over s squared here is the Laplace transform. All right. So let's go ahead and plug in our initial conditions. And so you can see that our expression here has a y of 0 and a y prime of 0. Okay. If we plug in for initial conditions, we have s squared y of s minus s times y of 0. So let's look back at our problem statement, and we can see here that our initial value, y of 0 is 1. Okay. We have s times 1, which is just s. And then we have y prime of 0. Y prime of 0 for this problem is also 1. And so we have just a minus 1 there. Okay. Y of s is still y of s. And then on the right-hand side, we have 1 over s squared. Okay. So that's step one. So step one, besides the derivative, fairly straightforward. So you're just taking the Laplace transform of the entire. Step two. Step two, what we're going to do is we're going to solve y. So y of s here, that is the Laplace transform of our solution, right? So remember when we solve for an ODE, we're solving for the function y of t, okay? And so, in order to solve it with Laplace, we need to solve it for y of s. Okay? The good thing here is that, we've eliminated all the derivatives because of the Laplace transform. And so we just are using algebras. All right. And so on the left-hand side, we have two terms with y of s. And so we have s squared y of s minus y of s. On the right-hand side, we have 1 over s squared. And And our two terms that involve the initial conditions, the minus s and the minus 1, I'm going to go ahead and move those over to the right-hand side. Okay, and so we end up with an s plus 1. And so I did this on purpose, just so that, we can isolate y of s on one side of the equation. And so we factor out y of s from that expression. We have y of s times s squared minus 1 is equal to 1 over s squared plus s plus 1. And then at this point, to solve for y of s, we're going to divide by 1 over s squared minus 1. We have y of s is equal to 1 over s squared times s squared minus 1 plus s plus 1 s squared minus 1. I'm going to make our lives a little bit easier because we know s squared minus 1 is equal to s plus 1 times s minus 1. Okay. And so if we do that, we get 1 over s squared times s plus 1, s minus 1, plus s plus 1 over s plus 1, s minus 1. We have an s plus 1, f plus 1, that's going to cancel out. And so we're left with s is equal to, just because it'll be a little bit easier for the partial fractions, I'm going to combine these two again. So we have 1 over s squared times s squared minus 1 plus 1 over s minus 1. Right. So that's step 2. So step 2 is down. Okay, so we've used algebra on our Laplace expression and we've solved for y of s. Okay. So technically that's the answer, right? So, when you're solving a differential equation, you're solving for y. And so we found y. Okay. But right now it's not really that useful because, we want this y back in terms of t, not in s. Okay. And so step 3. Step 3 is to invert y of s. To get y of t. Okay. So we've basically boiled it down to a partial fraction decomposition problem. So just like the first 3 examples. Right. So we have 2 terms here. The first term for sure, we're going to need to use a partial fraction decomp for that. The second term is actually good to go. So we have 1 over s minus 1. We know right away that that's going to be, we can invert that very easily. Okay. So I'm just going to ignore the second term right now. And then I'm going to work mostly on the first term, which is that monstrosity. All right. So if you remember from Thursday, I said, there's technically a step 2.5. And so the step 2.5, where you're probably going to spend most of your work, is doing the partial fraction decomp. So let's take this expression. I'm going to do the partial fraction decomposition. Remember, I'm going to ignore the second term because we know how to invert that already. All right, so if we write that term down, we have 1 over s squared times s squared minus 1. Right. So the reason I combined the denominator to s squared minus 1 just to kind of illustrate kind of both of our kind of special cases here. Okay. So let's take the s squared term first. And so we have kind of a repeated root, right? So we have s squared, s quantity squared. And so that's going to turn into 2 terms. 1 let's do the A over S plus B S squared. So both of these expressions right here come from the S squared. Okay. Right, so that was like example 2 that we did earlier today. Okay. So this one's not as bad, it's only 2 instead of 3. Okay. And then we have something here that technically is factorable, but we're going to pretend that it's not factorable, okay? Just so that you can, just to kind of give you a different look too, right? And so when you have expressions like this, you could definitely separate into S plus 1, S minus 1, and have 2 kind of extra terms there. So C over S plus 1 and a D over S minus 1. But another way that you can look at this, you can say this right here is a quadratic expression. Okay. And so this is going to be just like example 3. And so when you have a quadratic expression that you're trying to decompose, you just have to put a linear expression in the numerator. Okay? And so we're going to have a CS plus D over S squared minus 4. This from okay. So there's our decomp. Little combination of the example we did today. But now we just have to kind of go through the motions. Okay? So the first thing that we do in our decomp is we multiply by our denominator. Okay. And so we multiply by the denominator. On the left-hand side, we just get 1. On the right-hand side, we have A. So our denominator here is S squared times S squared minus 1. We have AS times S squared minus 1. My mouth said minus 1, but my pen said plus 1. Okay. And so we have B. The B is over S squared. So this is going to be B times S squared minus 1. And then we have CS plus D. The CS plus D is going to be canceled out with the S squared minus 1. And so this is going to be multiplied just by S squared. Okay. All right, so let's go ahead and distribute this. Okay. So just like before, we're going to distribute and then group the like terms. All right. So we have AS cubed minus AS plus BS squared minus B plus BS cubed plus BS squared. Okay. Right, so you can see here that we're going to have 4 terms, okay? 4 equations for our 4 constants. Okay, so we're going to have an S cubed term, an S squared term, an S, and a constant term. Okay. In the interest of time, I did want to do one more example kind of quickly, so I'm going to try to squeeze it in. I'm going to go ahead and skip to the system of equations. I apologize for this, but I just learned just a couple days ago that we're not having a lecture on Thursday, so I kind of have to squeeze stuff in. All right, so just like before, your S cubed term, S squared, S and 1. Okay. And so the good news is that our left-hand side here is quite simple. We have no S terms on the left-hand side. Okay. All that we have is just 1. And then for the S cubed term on the right, we have an A plus C. For the S squared terms, we have a B plus D. For the S terms, we have a minus A. And then for the constant term, we have just a minus. So again, 4 equations, it looks kind of intimidating, but here, it's not too bad, okay? And so from this, we get A is equal to 0. Equation 3, equation 4 tells us that B is equal to -1. And so this also tells us that C is equal to 0. And then B is equal to positive. So now that the decomposition is done, we can go ahead and plug this back into Y of S. Okay. And so Y of S, if we plug in our constants here, is going to be minus 1 over S squared. That is our B term. Then our D term is 1 over S squared minus 1. Okay. And then we can't forget the last term, which is 1 over S minus 1. Okay. I know I'm going really fast now, so I apologize. But hopefully, I'm hoping that you can kind of write these down, kind of go back and kind of go through them as you're doing them. Okay. I have a lot more examples in the notes too. And so I have one example that I don't think we're definitely not going to get to it all today. And I've actually posted another kind of notes, and should be notes 3A. That gives you kind of more examples of this. Okay, so I know we don't have as much time to do them over as many in class, but definitely check out the examples that I've posted as you're working on them. All right, so now that we're at this point, we can just simply invert this. Okay. So Y of t, if you have -1 over S squared, and so that's going to be a minus t. Now we have a 1 over S squared minus 1, and so that's going to be hyperbolic sine of t. Okay. And then we have 1 over S minus 1, so that's going to be e to the. So all of those are pretty much just straightforward table inputs. Okay. Any quick questions on this example here? Okay. All right. So I really want to get to this example because it is a little bit different. This one actually doesn't have any partial fractions in common, but it does have a complete the squares. So I did want to show you this. Go fast as fuck. We have y double prime plus y prime plus 9y equal to 0. Then we have our initial conditions. Y of 0 is equal to 0.16. And then y prime of 0 is equal to 0. So luckily in this problem, we don't have any inhomogeneous term. We just have a homogeneous solution. All right, step 1. Step 1, we're going to go across the entire equation. And so that's going to give us S squared minus S y of 0, y prime of 0. plus, here we have y prime, so we didn't have that last time. We have s, s, it's y at 0, plus s. All that's equal to 0. Next step, we're going to plug in our initial conditions. And so we have just immediately y prime of 0 is equal to 0. And so we can just cross that one out. And we know y of 0 is equal to 0.16. And so we plug those in, we get s squared y this minus 0.16 s plus sy s minus 0.16 plus 9 s is equal to 0. Okay. All right, step two. Step two, now that we've plugged in the initial conditions, is that we're going to solve for y of s. Okay. And so everything that's not y of s, I'm going to move over to the right-hand side. And so on the left-hand side, we have y of s multiplied by s squared plus s plus 9. On the right-hand side, we have 0.16 plus 0.16 s. We're going to divide by that quadratic term. We have y of s is equal to 0.16 plus 0.16 s divided by s squared plus s plus 9. Right. So step 2 is complete. Okay. Usually step 1, step 2 of these problems are usually pretty straightforward. Okay. Step 3 is when things get a little bit tricky, so that's when we have to invert. Okay. Right. So this is the main part I wanted to get to in this problem, because this is something that we probably did examples of this last week, but I want to make sure it kind of gets drilled in. All right. And so what we have in this problem, if you look at our denominator here, is we have kind of a quadratic expression. Okay. We're kind of stuck at this point normally because we can try to do a partial fraction decomp, but the partial fraction decomp won't get anything. There's nothing to decompose, right? We just have one term or one expression that's a quadratic. So we cannot partial fraction decomp. Or you can, but it doesn't help us, right? Because it doesn't help us get closer to a table value. Okay. So this is going to happen often, okay? And so oftentimes you're going to have a quadratic denominator that is not going to be, doing where partial fraction decomp is not going to help. Okay? And so in these situations, oftentimes this occurs whenever you have basically damped oscillations. Okay? And so what you have to do instead is that we're going to complete the square on the bottom. Okay. And so we have s squared plus s plus 9. Okay. And so the way to tackle these problems is to look at kind of the first two terms here. Okay, so the s squared, the s terms, usually be s squared plus something times s. Okay, and you want to complete the square for this. Right, so it's 9:45. You know, I won't be able to take this all the way to the end, but I do want to get you to the point where you can do it and give you a big hint for how to complete. Again, you know, all the details for these examples are in the notes. So you know, I hate doing this because you know I usually like to cover everything in the lectures, but you know, kind of a weird situation with the guest lecture. Okay, so if we complete the square, okay, the way we actually complete the square with an s squared plus s is to add a 1/4 actually. Okay. Okay. Because if we do this, this becomes an s plus 1/2 squared. I think last time I gave you a formula to complete the square. And so if you plug into that formula, that's basically what you get. But remember, you know, when we complete the square, you know, we can't pull those extra constants out of nowhere. Okay, so we kind of took that 1/4 and we kind of pulled it out of nowhere. And so we need to balance that out by subtracting a 1/4 as well. Okay? And so what we get from this is y that we need to do 0.16 s plus 1 divided by s plus half squared plus, we have a 9 minus 1/4, so that's going to be 35 over 4. And what I'll leave you with today, you know, I know I'm already going a couple minutes over. Okay. If you look at this denominator here, this should look like 2 terms in your table. Okay, so it's going to be the very last 2 terms in the bottom right. It's going to be e minus at cosine omega t and e the minus at sine omega t. Okay. And so if you look at the Laplace table, it's going to look like those 2 terms. Okay. And so now that we've gotten it here, it's just kind of more just manipulations to make sure that you can do those inversions. Okay. But that's basically your goal. And so for these kind of Laplace ODE problems, you either are going to do partial fraction decomp, which we covered in detail today. But if you have kind of a quadratic denominator that you can't decompose, this is probably what you're going to do. So you're going to complete the square and try to get it into this kind of paying sinusoid. All right. Any final questions on this before we wrap it up for today? Okay. All right. So thank you guys for staying late. I know I went quite a bit over today, but I wanted to make sure that you got this so that you can do this on the homework. Okay. So get started on homework 3. You can let me know if you have any questions. I have office hours tomorrow and Thursday. And then remember, Thursday is our guest lecture. Okay, so make sure you come for that. Come with questions. And so you usually those guest lectures and raise questions. Hope you guys have a good day, and I will see you all on Thursday. Make sure you guys talk.
With the solve group. Yeah.
Crystal, any final questions before I close the call?
Lower class people. Like us?
Okay. All right, so I'm going to close the call. So I'll see you on Thursday for the guest.